Yeah, I'm going to talk about um, two projects involved about physical consistency and machine learning in atmospheric chemistry today. Um, and kind of a general overview of the field is there's been a lot of work that Makoto has done and some others investigating can we have machine learning emulators of the computationally expensive chemical integration. Uh, and where this work that I'm going to talk to you about today fits in is hybridizing domain knowledge and our knowledge, physical consistency with these data-driven tools. And so the first project that I'm going to talk to you about, which was finally published in James last month, is Advecting Superspecies, which is essentially automated lumping, but also in a way that conserves mass. And we did this to enable detailed SOA process models in an air quality model to improve their PM prediction. And they're working on getting that up and running for operational forecast these days. The second project that I wanted to talk to y'all briefly about is the mass conserving framework for machine learning. Um, Rather than predicting how our properties of interest change, like uh, concentration, we first predict how material flows between our properties of interest. So how atoms flow between molecules. And then we can use domain knowledge to make sure that this is balanced so that the machine learning emulators conserve mass, atoms in the cases that I've worked on. And I'm going to briefly touch on its relevance to graph theory and network connectivity, because as you saw from that screenshot of my GitHub, I am pushing my graph theory agenda on the field. All right, cool. So let's talk about project one. I know Bob's here for that. I think you all are too. So there are other chemical transport models besides Geoschem. One of them is called Lotos Euros, and it is used in the CAM's operational forecasts for Europe. However, it underestimates PM 2.5 kind of a lot. There was a paper last year investigating that and kind of um, pointing to lack of good organic aerosol representation as a cause of that. It's just left out of the model, or it's just one passive tracer, one single tracer for all OA. So another thing is that these ensemble cams forecasts that I just mentioned require like more detailed organic aerosol representation than this. And that's so Lotus Euros needs to have that in place by the end of 2023, though that target has changed a few times. Lotus Euros does have a pretty realistic process-based model, which is a volatility basis set approach that since we're methods based, I'll get into that in a little bit. That's high detailed, but it's also high dimensionality. And those tracers need to get passed around throughout all the operators in the model. And especially they were doubling the wall time of advection, which in Lotus Euros is also one of the most computationally expensive operators. So my question was, can we use data-driven methods, maybe machine learning, maybe matrix factorization, to find this like some sort of lower dimensional set of superspecies to transport instead, and be able to map between these superspecies and the full VBS volatility basis set space. And this is my little cartoon of the superspecies, not to scale. And I just wanted to touch on similar how this relates to similar efforts by Makoto, who's focused on neural network autoencoder architecture that both for CBMZ, Mosaic, and the Superfast. And this neural network architecture solves, like, integrates forward in time in this low dimensional space, which is kind of not, to my understanding, also relevant to, manifold work in atmospheric chemical mechanisms from a few decades ago. We're bringing it back. I think that's pretty cool. And at the end of a paper published in 2020, the question was posed: how does this chemical latent space, aside from the chemical operator, how would this interact with other operators? How would this be transported in a 3D model? I was like, that's a great question. Let's look into it. Okay, so here is a schematic of the complex volatility basis set in Lotus Euros. And if it looks like a lot, it's because it is. And that's my point. There's a lot of tracers here that that need to be handled individually by all the operators in the model. So maybe I'll take a little bit of time just to break this down, because Bob, you might be curious about this, and maybe we can talk about later. We can talk about the differences between this and the SOA scheme that you're looking at. But Lotus Euros uses 4 volatility basis sets, and since I haven't defined volatility basis set, let me get into it. There's a ton of organic species in the atmosphere, and some of them can partition, like, appreciably between particle phase, or some sort of condensed phase, and gas. So the volatility basis set essentially bins particles not by size, but it bins species by their saturation vapor pressure. So what's their tendency to be in the particle phase or the gas phase? And Lotus Euros takes that a step further and has 4 different VBS, volatility basis sets, 4 different types of compounds. One is POA, so primary organic aerosol, that's emitted from non-electric vehicles, among other things, gas mobiles, etc. And this primary organic aerosol can age in the atmosphere, usually, to become less volatile. So the dashed lines here represent kind of like a thermodynamic relationship, where the filled in circles are particle tracers and the not filled in circles are gaseous tracers. And then the solid lines actually represent chemical aging, oxidation with, reaction with hydroxyl radical, a classic. And those are 2 of the 4 volatility basis sets. And then they add even more dimensionality by having other anthropogenic volatile organic compound precursors that can also age and eventually become less volatile. And also for biogenic SOA, and like a VOC precursor example is isoprene. So that's the Lotus Euros VBS scheme, and it's off by default in the model. But we want to be able to include it, but maybe represent it in lower detail in places where we don't need the full chemical complexity, like transport, which is kind of some bulk movement of stuff in this grid cell to stuff in that grid cell. So we looked into a lot of methods, but like one of the key goals here was that it would be physically consistent and interpretable. So we can resolve other equations in other processes and operators using these superspecies. And so people in the aerosol science community use this thing called positive matrix factorization. Since I had taken a few machine learning courses that focused on like image processing, I called it non-negative matrix factorization. The semantics of the differences there we don't need to get into them. So we took non-negative matrix factorization and we kind of augmented it a little bit. We wanted to, rather than it's a linear method, I just want to say, I was talking to Danielle Jacob about it last year, and he's like, it's non-parametric, or he's like, it's parametric, right? And I was like, I don't know what that means, but it is linear. And so our approach has made it so you can compress to superspecies for advection online in the chemical transport model and decompress after. Note that we're not actually optimizing the data-driven tool. I know Makoto has done work in that space. We're optimizing beforehand, but we are compressing and decompressing online. We really wanted this to be physically consistent, like I said, so this preserves information on whether or not the superspecies is in the particle phase or the gas phase. And since it's linear, it's really easy to conserve mass. You can scale things to make sure that the amount of gaseous superspecies is equal to the total amount of gaseous superspecies equal to the total amount of gaseous VBS tracers. And that won't change the shape of the distribution. I'll show you kind of what the volatility distributions look like in a second. But that's kind of the appealing part of the linear model. So let me just kind of demonstrate what the distribution looks like. First of all, if you look at the x-axis, those are your those are the volatility bins, and the y-axis is your concentration. And I want to direct your attention to the legends. So the bottom maroon one is our reconstructed distribution after decompressing the superspecies, and the top is just the VBS approach. We might still get the distribution slightly wrong, but with this mass conservation approach, total organic aerosol is conserved, and the concentration of the gas phase tracers is also the total concentration of the gas phase tracers is also conserved. And this works at in any condition, in all conditions. So at kind of like higher aerosol loadings of decently populated areas such as the Netherlands, that's Cabal, or Macehead, which is on the west coast of Ireland and is described as a pristine location. So mass conservation is exact using this method. Another thing that I wanted to talk about is we found that there's not a we couldn't find some sort of general model that would work in all conditions, and sometimes it was beneficial. We found that it was beneficial to optimize the superspecies for specific seasons. One thing that we were noticing was when we used this approach and trained it on data from the winter, it was really overestimating biogenic SOA. And it was overestimating biogenic SOA over forests and at night. Now, we're training it on data from a European domain, not much biogenic SOA in the winter. All the leaves are gone. And so this was affecting the total, this was overestimating the total PM count too. These graphs just show on the left, this shows total organic aerosol, but it was really driving the PM guess up. So then we retrained the superspecies on summer data and saw that we could really reduce this bias. This is slightly different from the work that Makoto did, also investigating like the seasonality of or season-specific machine learning models. I think Makoto, if I'm correct, yours was a way of doing kind of like a bias reset, and here I think this was actually the winter superspecies were just completely incapable of modeling biogenic SOA because it was underrepresented in the winter training data set. I'm not sure if that's if you zoom out enough, it's probably the same problem. But just wanted to point out the similarities and kind of the distinctions there.
I have just a quick question,
Yeah, yeah,
just so we can maybe contextualize the method. So
totally.
you're doing a non-matrix factorization, is that right?
No,
Here?
yeah, non-negative matrix factorization. That's correct.
Yeah. And so you use the word training. And so does training mean you learn the weights of that NMF, or
Yeah,
like what, I guess when I hear NMF, I hear kind of like it's just like a method you do onto something. So it's like you do a linear regression and it's all the same for every kind of data. But an NMF, is it more like you have a matrix and you're learning those weights? So it would be very different each time? Or is it something where Bob can apply this to the GS chemical species and it's like a PCA? So each time it's kind of like the same operation and you get a different thing.
it's not PCA. There's no closed form. So you're gonna get a different answer depending on your initial guess of weights. And so training in this context, there are multiple ways to like converge to I have a no equations rule on slides. But I'm happy to share that later if we circle back around to it. Basically there are multiple ways of getting your weights. You're correct. It is training is getting those like optimal weights that best recreate the high dimension from the low dimension representation. Um, but and I think there's the two ways that I think are used in the back end of non-negative matrix factorization are gradient descent, which um, we know will spit out different answers depending on where you start, and multiplicative update, which is much faster and I think might be the default in scikit-learn. Um, but the main point is that it could be different depending on where you start. And that's why I call it that's why I called it machine learning for a while. The main thing is it's not like PCA because it doesn't have a closed form.
And sorry, just one follow up, just so in the interest of, keep using Bob as an example here, but let's
Totally.
say we have, like 5 years worth of geoscam at hourly resolution, a ton of data, enough to, run this algorithm. Would you suggest then of creating like one generalized algorithm that has all this data, or would you say we should maybe create like a lookup table over North America winter, and then because geoscam can like store this, and it's cheap because they're just all numbers. Would you suggest like one generalized algorithm that this is powerful enough, or do you think the specificity is really needed as you kind of show in this slide?
I would say the latter, absolutely. There's plenty of open questions here, but if I can already conclude that we want to have specialized models. What we did during this project is we started trying to have some sort of thing that would do all four classes, all phases, right? All 58 tracers just get compressed into some set. And then we just kept on adding cross sections. So then we started doing it so VBS class specific. We want a biogenic SOA specification. And then we want particle and gas phase because we have this mass conserving process. Why not apply it to both particle and gas phase so we conserve total particle count and total gas phase concentration? Um, so yeah, I would say I would conclude that you want to have specialized um you want to have an ensemble of specialized small matrices, and ultimately that's what the output of the super species approach is. They're just matrices, and they were a lot of small matrices. um and something I like about those matrices is you can think of the weights there as, since it's just a linear method, you can think of the weights as like the VBS tracer composition of each superspecies. And that's nice for insight. That's actually how PMF is used in other applications. Figure out how um, figure out what the composition of this high dimensional space is in this lower dimensional latent space. All right. This is usually the climax of the slide when I present it to the Lotus Euros people because they care about speed. So the VBS pretty much doubled the wall time of it, and they're like, okay, we can't run simulations in Chem's operational forecast with this. Super species kind of sped that up by like 50 to 80%. And that is within their computational constraints. So it just scales linearly. The advection operator is a for loop over all species. So the more species you require to be advected, you can already kind of get a sense of the slowdown that you would expect. So yeah, that it sped things up. They were happy about it, and now they're just testing it more and looking into including it in operational forecasts. So a few methods and takeaways. So an extended conversation I had with my collaborators is why non-negative matrix factorization over an auto-encoding neural network. Well, we tried the autoencoder neural networks and got early stopping. And, I'm not sure if this is because I had a bunch of hyperparameters that were, kind of wrong for the data that I was using. But I think of early stopping as a symptom or a sign of overfitting. And that might mean that the neural networks were kind of already too complicated. I like simple. And so rather than kind of like wrestle with the neural networks, we wanted to see how well this linear method would do. And then kind of just back to the methods, it's way easier to write Lotus Euros routines, subroutines that'll load in matrices. And a neural network isn't that different, but it's a lot larger in terms of parameter space and connectivity. And I'm not sure. It seemed like it was easier to write my own subroutine to load in matrices than figure out how to use the Fortran Keras bridge or C tools. So that's kind of like the methods that we explored. Kind of a bigger picture thing is this project was proposed to me as they're like, the VBS scheme slows down Lotus Euros. Let's make a neural network emulator for it. And that would have, so something that memorizes the partitioning or that emulates the partitioning. And that would have like sped things up by like 0.2%. So like that would have been answering the wrong question. And I think it's important that we don't use think of machine learning as this black box that we can throw at anything and it'll solve the problem, especially if we don't do the work to actually figure out what the problem is. So much more relevant here was just finding some sort of automated lumping method and finding a way to decompress it to the full chemical detail when we want it, rather than trying to emulate the processes that we have good process models for. So yeah, those are my takeaways from the advecting superspecies work. I'm going to blast through this project real quick, and then maybe we'll have like 5 minutes for discussion. Does that sound good? All righty. So conservation laws in neural networks. I talked about not doing neural networks, but I do also do stuff. I also wrestle with neural networks on a daily basis. And these neural networks don't inherently benefit from, our rich domain knowledge of atmospheric chemistry. They're not always interpretable. They definitely don't inherently conserve mass. Not that the chemical integrators always do either. So this mass conserving framework that Tony Wexler conceived of a few years ago is really quite genius, and it's just a flux tendency relationship. So rather than predicting the concentrations or changes in concentrations for an atmospheric chemistry application, we can predict extensive reaction. So integrated reaction rates that we can use our domain knowledge, domain knowledge of the reactions in that system, our stoichiometric balances to ensure atom conservation. So we just did this on my little toy Julia photochemical model. And hot off the press last week, this was a surprise to me, but I saw that this has also been applied to a complex SOA scheme where I guess they were predicting fluxes between bins of 17 volatility bins and 20 sectional bins. So massively dimensional. About 1,000 particle related tracers because there were multiple species. So I just found out about that last week, was really stoked to see it. If you're interested in hearing about it, talk to me. Tell me about your application. Are you using a machine learning emulator? Is it not conserving certain properties? Well, you might be able to use this framework. If not, I have other ideas for how to conserve properties in data-driven models. So yeah, in any case, talk to me. So we found that this also kind of improved predictions over like a naive neural network, and more than just conserving mass, it also kind of improved species level accuracy. And I think that's because we're building domain knowledge into the physics constrained NN. This balance, this mass conserving framework specifies which species interact with other species in reactions. And so that's encoding the like graph locality of the chemical system. Yeah, here are some of my references. Apparently I didn't update them from the last time I gave this presentation. And so some takeaways, modern data science, machine learning, and classical methods, that's a false choice. We can do both. And I'm really interested in making that happen. So yeah. Cool. That's
Great talk,
all.
Obin.
Thank you.
Oh, great talk.
I love it. We're very skeptical of machine learning and the machine learning subgroup. So I think it's great to think critically about which algorithm to use. And if a matrix linear algebra method works, it's so much better than using like the massive neural networks. Like I think it's a really great approach. And that merging of the two that's the hard part. We're thinking about ways to trade off and get the benefits of both. That's a nice way to go in science. I don't have a specific question though. Yeah, but just a compliment.
Thanks. So yeah, happy to talk about either this mass conserving framework or the super species or the VBS. Fire away, everybody.
Thanks, Obin, for a great talk. So the GeosChem, Chem, just for, I can send you the details later, but the GeosChem Chem SOA classes or volatile VBS classes are somewhat similar. There's 4 of them. And I was looking at like how to reduce them to something tractable in KPP. But the other thing that we have been struggling with is the halogens. So like there's been some talk, and I think Christoph has been working on this at GMAO, of how do you like lump like halogens in the stratosphere for transport, because it may be there may be a way to gain like some instead of transporting like several species, you can just transport families. But how do you do you just transport like the BRY, CLY, or is there some other way of lumping them together that makes more sense? So I'm wondering if it could be applied to like that type of problem as well.
So Christoph actually hired me to do that.
Okay, yeah.
That was kind of the premise of me starting at GMAO,
Okay.
and we looked into that. We started just with a blacklist of species that we thought had like, slow chemical lifetimes that might not be important in like a 5 to 10 operation or forecasting product. We got kind of into the nitty gritty of the timing and realized that a lot of the wall time that we were previously attributing to advection was actually just coming from a VM barrier, like a parallelization barrier. And that parallelization barrier doesn't come until advection, until grid cells need to talk to each other. Grid cells across CPUs need to talk to each other. But really where the load imbalance, the unbalanced slowdown of certain grid cells happens is in twilight chemistry.
Oh, okay. Yeah.
So, I mean, it might be different for Geoschem. I mean, GeoCF is using this MPI framework on Discover, and OpenMP has like shared memory, I think, right? So this load imbalance might not be as relevant. Yeah, I think even if it doesn't save that much time, it might be still good to just like, transport lumped species, but we've kind of pivoted away from that, realizing that advection isn't taking as much time in GeoCF as we thought.
Okay. All right. Very good. Thank you.
Yeah. And I definitely, would like to hear more about the SOA scheme that you're implementing in Geoschem. The Lotus Euros one is pretty simple from a chemical perspective. It's really just reaction with hydroxyl radical.
Right. Ours may be a little bit more complex because we have OH03 and NO3 oxidants.
Okay.
So there's more reaction. So for every VBS scheme, you have those reactions, and then there's like some branching into like high NOx and low NOx regimes. So it gets a little bit more.
Oh, actually, Lotus Euros, I didn't think of a good way to represent that, but we also have the low NOx, high NOx split, and that's kind of just implied in the this little tree here.
Oh, okay.
How that works depends on our NOx concentrations.
Right.
One thing that I'd like to point out is like in this project, we learned not just me, everybody learned a lot about the VBS. And we figured out that we were like carrying around tracers that like never got mass ever because there was no chemical aging after this bin. And no way of getting there from the VOC precursors. So,
interesting.
Always good to take apart these models and see how they work.
Yeah, I agree.
I think we'll call it there because we're coming to the hour. But thank you so much, Obin, for this great talk. And we'll meet again in a month. See you all.
All right. Thanks everyone.
Bye, everybody.
Bye-bye.
Bye.